So we try something a little bit different today, just for kind of trying to be able to get through as much practice as we can. Instead of me kind of moving around, going up back and forth between here and the board, I'm going to use this dot cam. We'll see if you guys like it. I might start using this a little bit more. The reason why I don't use it is to create some incentive to show up to class, because if this is all in the recording, you can see everything I'm working on, right? Then there's not much an incentive to be here. Well, I guess the iClicker points, but I like to think that it's kind of useful seeing this work through in real time. But for this exam review, I want to make sure I have everything recorded. So if you're working through those practice exams, you can always go back to a video and see exactly how it's worked through. So you'll start seeing a bunch of videos get put up on our YouTube kind of channel. And I try to specify what practice exam and what questions. I've already put up all the questions from exam A, like those were put up last week. So through the different sections today, I've been working through practice exams that have similar questions. And so I'm hoping to think I've worked through, I'll have videos up for every single question from practice exam B as well. If not all of them, the vast majority, okay? But we'll kind of work on them here today as well. Unless you have very specific questions, like over either practice exam, we can kind of cover those. But if there's no specific questions, or once we work through the specific problems that you guys have questions on, I'll kind of pick and choose questions from practice exam B to start working through, okay? So I think I mentioned, I was thinking about doing a short answer portion, but I don't really want, it kind of makes the exam a little bit longer, and I want to make sure time's not an issue. So I have the exam written. It's going to be 20 multiple choice questions. You know, a lot of these things that we'll start talking, we'll see today, a lot of them you can rule out a lot of the answers. So I think in some ways that actually helps you a lot more than a short answer question if you're completely lost. At least you can kind of narrow some of these down to like 50-50 chances. Okay? I also will probably be kind of nice and maybe have like a bonus question or something on there like we had before. In the exam, I will give you a standard normal Z table, student T table, and that form in the sheet that is currently up under the practice exam materials on Canvas. Okay. Other than that, before we kind of jump into things, is there any logistic questions about the exam?
All paper, no Excel.
Yep, so it'll be on paper, no Excel. You can write on the exam. I'll have blank paper if you want some.
Are you checking for where?
Nope, so it's just correctness. Whether or not you get it correct, or you get points if you get it correct, no points if you don't. Okay.
No open response.
There won't be any open response on this one. Nope. I think on the final, I will have a few more open response. Some of the material that we look through will be a lot more interpretation. So that one will look a little bit different, but for this one, kind of strictly multiple choice. Okay. Any other logistical questions? Make sure you bring a calculator, unless you're, you know, crazy smart and can do all the math in your head, which is great. All right. More questions? Okay. Are there any specific questions that you would want to work through on either practice exam A or practice exam B? Anyone taking a look at those and had specific questions, we can start with those. Otherwise, I'll start kind of picking and choosing. Okay. So one thing I'll mention, because I don't want to forget it, and I've had a couple questions about it. Also on the Connect assignment, there was an error on 14. I have an announcement that basically gives you the answer. So if you're like, I swear I'm doing it right, it's not counting as correct. I had that announcement up there that gave you the correct answer for that one. There's something wrong with the algorithm, okay? So other than that, let's go to practice exam B here. I'm gonna start out on problem number 14. Yeah. So let me think how to deal with that. If you turned it in, you didn't get that right, send me an email and it's probably easiest for me to go through and manually change those for you. Yeah. Yeah, so I don't know if that announcement didn't pop up on for some reason, not pop up on Canvas, but it's sitting up there. It was kind of up there last week. I think I didn't mention it in class, but it's been up there. So yeah, if for whatever reason you turned it in ahead of time and you didn't get that 14B correct, I believe it was, send me an email and I'll manually go in and correct it. So we'll start with 14. I will put up a video that is me working through questions very similar to 14 through 19, but for a slightly different problem. So for us, we're going to work through one where I've got the IQ of Ball State students. I know they're normally distributed with a population standard deviation of 15. So I'm given a population standard deviation. I've got a sample of 49 students, and I find a sample mean of 109. Okay. Now, the other kind of style I worked through with the other section was the exact same type of problems. But if instead of having a known population standard deviation of 15, I only had a sample standard deviation of 15, the way we would answer these questions would change a little bit. So just kind of recap before we even get started in here. We've got really three types of problems we can do hypothesis testing and confidence intervals for up to this point. I could have a sample mean, and I know the population variance, or kind of say it different, right? I could also just know the standard deviation. If I know one, I know the other, right? The variance is just the standard deviation squared, and standard deviation is just the square root of the variance. I could also have examples where I'm looking at proportions. In either of these scenarios, if I want to do confidence intervals or hypothesis testing, I get to use the standard normal or the Z tables. Okay. The only other types of problems we had is when we have the sample mean, but only have a sample variance or a sample standard deviation. In this case, we're going to use that student t distribution, because when we calculated that sample variance divided by n-1, right, it inflated our standard deviation a bit. So we didn't have standard normally distributed z values, right? 0 mean, 1 variance. We had student t distribution where the mean was 0, but the variance was slightly higher than 1. Okay? So the problems that we're going to be looking at, we were given a known population standard deviation. Okay, so we should right away know we should be looking at that standard normal distribution. Okay, so if I'm looking here, should I be using the student t or the standard normal for this type of issue or this type of problem? Well, I should be using the standard normal distribution because the variance is known, or sorry, the population variance is known. The one I worked through in my other section, which I'll get an additional video up, is how we would work through these if I only had a sample. Sample standard deviation, in which case I instead would have to use a student t distribution. Okay. So for this one, right, we've got a known population variance or a known population standard deviation, right? Those kind of are synonymous. If I know one, I know the other. Okay. So we're going to be using that standard normal. And the first question we're asked is, how would I build this 90% confidence interval? Okay, for where the true population mean IQ actually is. Right? So I'll go to my formula sheet. And here, this is for something else. So go to my formula sheet. I've got 3 confidence interval equations over here, and then 3 test statistic equations. Well, I'm looking at building a confidence interval. I had a sample mean, so hopefully I can identify it's going to be one of these two. Well, I had a known population standard deviation. So I know the population standard deviation, or I know the population variance. So this is going to be my confidence interval equation that I'm using. Okay. So I'll write this down, and then we can kind of think about, or we can kind of plug our values in. There we go. All right. So here's my confidence interval equation. All right. So the first thing I need is my sample mean. Okay. So we go back to the problem. My sample mean was 109. So 109 is that sample mean. I'm then going to go a certain amount of standard deviations to the left and right to build my upper and lower bound and construct this confidence interval. All right. Well, the next thing that my formula sheet reminds me that I need to do, I need to go a certain number of standard deviations away. Right? Well, if I was going to build, what level? 90% confidence. What's the value of my alpha here? So if I want 90% confidence, the area outside is 10%, in decimal form, 0.1, right? We're kind of dealing with probabilities there with alpha. So I need to go find that number of standard deviations, that z value that gives me alpha over 2 on either side. So alpha is the total area outside my confidence interval, which means I've got half of alpha on each side. So I actually want to look up that area of 0.05 kind of on each side of my confidence interval, or kind of think about it as on each of my tails. So I'm going to go to my standard normal tables. Okay. I want that area of 0.05. So I'm going, if I know the area in the tail, that's the values in the middle, right? So I've seen a lot of confusion of when I'm looking up using the standard normal table. The row and column headings are only if you actually know the z value. For a confidence interval equation, right, we were trying to find this z value that gave us a desired area in the tail. We don't know the z value. That's what we're looking up. So I shouldn't be using the row and column headings. I should be looking up that area in the tail that I want in the middle of this table, right? So I'm going to hunt for 0.05. Looks like it's the closest I can get are these two values, right? So negative 1.64 and negative 1.65. I'm kind of somewhere in the middle between those two. So we can kind of use the larger of the two, or negative 1.65. However, right, that positive negative, the number of standard deviations above and below that we want to go, is already built into our confidence interval equation. So we just need the actual value, the absolute value, sorry. Okay. Any questions on that? Now, what's another way I could have been a little even more precise here? Kind of a shortcut, and this really becomes a shortcut when we're looking up critical values for, oh, come on. All right. I guess I got to reopen this. So let me go here. I think I've got the student T table sitting out here. There we go. So I could have used the student T table, right? And just went all the way down to this very last row. And we said the very last row here is going to kind of show me my comparison, my benchmark standard normal values, right? If I did have a degrees of freedom of infinity, which would mean I'd have to have an infinite sample size, which doesn't make any sense, right? But if I did, I know that my student T at that point would have completely converged to the standard normal distribution. So we said one shortcut is we can use the last row of the student T table to look up different standard normal values. So the area I wanted the tail was 0.05. So I go up here. This is the area that I wanted the tail, 0.05. They come down all the way to that very last row, 1.645, right? I can be a little bit more precise. I can kind of go out to that third decimal if I wanted to, right? Now, rounding to the second decimal will never give you an answer that is one of the other four possible answers there. Like you might be a little bit off to the third decimal, but it'll be really close to where you can identify what is the correct answer, right? But if you want to be a little more precise, we can use that last row of the student T table. From there, it's just a matter of completing the rest of our confidence interval formula. We'll take the square root of our population variance over our sample size, okay? Well, if we look at the original problem, we were only given a population standard deviation. So in the formula sheet, we had sigma squared, but all I really have here is the standard deviation. So all I have is sigma. So when I'm plugging this in, I can put in that 15, but I have to remember that I still need to square that value because I don't have the variance. All I have is the standard deviation, or all I have is sigma. Okay. The only last thing I then need to do is divide by my sample size. So divide by 49 there. And now it's just a matter of getting this entered into our calculator, right? Add this margin of error to get our upper bound, subtract this margin of error to get our lower bound, okay? Now, one thing I would do if I was working through this one is probably try to calculate my margin of error first, right? Just to make it a little bit easier. On these confidence interval ones for, just the order of operations, for whatever reason, it's easier to work backwards. So in your calculator, take 15, square it, divide by 49. Whatever that value is, take the square root, then multiply it by 1.65. Right? If you do that, I don't have a calculator here, but I've got Excel. So I'm going to do this behind the scenes just to come up with what that value would be, unless somebody can beat me to it here. Squared 15 squared divided by 49. So we should get, excuse me, 3 point, no, I already forgot what it was. 3 point, there we go, 525, right? That kind of represents my margin of error. So then I would just take 109 plus 3.525. That gives me my upper bound. 109 minus that 3.525 will give me my lower bound. That way I don't have to like enter it into my calculator twice, right? Once I get the value once, I know I'm just adding that to get my upper bound and subtracting that margin error to get my lower bound. Oops. Any questions over anything there, kind of constructing these confidence intervals? Okay with this? Okay. So the next question says, all right, you've constructed this confidence interval, but maybe you want to do some hypothesis testing, right? So maybe we've got something like, I want to test for whether or not the average IQ of a Ball State student is different than the national average of 105. Okay. So what would my null and alternative hypothesis be here? Well, whatever I'm trying to find, whatever I'm trying to test for, that's my alternative hypothesis, right? So if I want to know whether or not that true mean IQ, right, of Ball State students is different than the national average of 105, anytime I see this term different than, I should be thinking about what sign of my alternative hypothesis. Both sides matter. So all I'm really saying there is it not equal to, right? Is it different than or not equal to this national average value of 105? So right away, seeing that term different than, we should have been thinking about C or D. From there, identifying the value, whatever value you find from your sample, that's your evidence that you're using to either support or go against the null. So your sample mean or your sample proportion should never be the value in your null and alternative hypothesis, right? I mean, if it was, that would mean what you assumed to be true, you found exactly that value from your sample. That's very unlikely, right? In fact, the probability of finding that is actually technically zero, theoretically. Right? So whatever your sample mean or sample proportion is, that value should not be in your null and alternative. The null and alternative value is going to be something that you're trying to test against, test for. So the null, to complete this, will just be the exact opposite of what you're wanting to test for. You stack the deck against yourself. You assume it's exactly equal to 105. So now if I'm assuming that it's exactly equal to 105, if I see a sample above or below 105, that could go against the null, right? So I've got a two-tailed test here, right? Not equal to sign, both sides matter. Okay. Any questions on that? So one thing I might do on the exam, I've written it, so when I say might, I'm probably saying this for a reason. If I ask you to identify a null and alternative hypothesis, sometimes what I'll do on the very next problem is then give you, okay, maybe that's what you want to test for, but now assume that the null and alternative hypothesis is this, right? I'll give you a null alternative. That way you can't get cascading errors. If you thought it was a two-tailed test and it's actually a left-tailed test, well, now your critical value is going to be screwed up, your p-value, your rejection decisions. So if I ask you to find a null and alternative hypothesis, the very next problem, I then might give you, okay, for the next three questions, assume that this was the null and alternative hypothesis. When I give you that assumed true, like null and alternative, don't read into it at all. I'm doing it for completely different reasons other than whatever the correct answer was in the problem where you had to identify. I'm just doing it to make sure everybody's starting off at the same point. Okay.
Can you kind of fill in and get your response? What you're saying?
So what I'm saying is this, right? We just had to identify what the null alternative was. We just found that it was D. On the exam, what I then might do for question 17, where I'm asking you about critical values, is I might do something like this. Assume that instead, the null and alternative that you were testing was, I don't know. Oh, I forgot to write the alternative here. All right. I might give you something like this. So that way now, we're not using the correct one, right? It's like we're almost starting the problem over so that even if you got this wrong, at least now we're all starting off in the same foot. Right? Now, don't read in this at all. I'm choosing different numbers a lot of the times. I'm making it the complete different type of test, or maybe I even make it the same as the one before, but I changed value. I'm just making sure that we're all starting out in the same point when I give those assumed true null alternatives. Okay. Does that make sense? Any questions on that? I don't want that to trip anybody up. So don't read into those at all. It's just to make sure that everybody's starting off on the same foot. Okay? But here on this practice exam, because I could give you like, I kind of had the answers in a different document, right? I don't have to do that, right? We can just keep using what the actual normal alternative was. Right? So if I wanted to find critical values here, I've got a two-tailed test, and I had a known population standard deviation. So this was a situation where I can use that standard normal distribution. Okay? So if I'm dealing with a two-tailed test, I've got this standard normal distribution. Now, when I'm finding critical values, the very first critical value I'll be looking up is for the alpha of 0.1. I think the question even says, find the critical values for the 10, 5, and 1% levels, which would correspond to alphas of 0.1, 0.05, and 0.01. So we'll look up the first critical value first. But for a two-tailed test, evidence on either side matters. So we're actually going to have a pair of critical values at each alpha threshold we set, right? Because one way to think about the critical value, with a p-value, I think I told you it's like the threshold probability. If we see anything that's even less likely than this threshold alpha of 0.05 we set, then we can reject the null. Here, we can think of the critical values. They're just z-values. So the interpretation of a z-value is the number of standard deviations away from whatever that assumed true population mean was. So with the critical values, what we're really saying is these are like my threshold number of standard deviations away. If I see sample evidence that's any more standard deviations away from the assumed true value than these thresholds I've set, then I'm okay rejecting. Which is why we kind of then said, my rejection region would be kind of, if I see a test statistic anywhere in those tails or anything more extreme than my critical value.
Rejecting the alternative, right?
So what we're always testing, like we're trying to make a decision for, is remember, we've assumed this is true. So this is what we're trying to say if we can reject or fail to reject. Now, if we can't, the only evidence that's interesting is evidence that actually supports the alternative. So it's not, I want to be careful here. It's not necessarily that we're saying we accept the alternative. It's just we're saying we found evidence to support the alternative, and so we're going to reject what we assume to be true. Questions up to this point? So we want to find this pair of critical values that gives us alpha total in the tails. Okay? Well, with a one-tailed test, all of alphas just in one tail. We only have one tail. But if we have two tails, alpha is the total area in the tails now. So on each tail, we'll have alpha over 2. So it's going to look very similar to confidence intervals, right? I mean, almost exactly the same. So we want here 0.1 over 2 in the tail, or 0.05. Well, we just looked this value up for confidence intervals. It's not going to change at all. I mean, we can look it up again if we want to. All right, we could go use these t-tables, kind of use that last column. So it's not really cheating, but it's just kind of using a shortcut. The area that we wanted in each tail, alpha over 2, is 0.05. So we're going to be in this column here. Go all the way down to the last row, which gives us our standard normal value. So we've got what, negative 1.645 and positive 1.645. That will be our pair of critical values at the 10% level, or for an alpha of 0.1. So at this point, we really could kind of stop. We've already identified where is it at? Right here. We've already identified the pair of critical values for the 10% level. Now we could look up the other two. And if we use that shortcut, it's pretty easy to do, right? I mean, here I could look up, instead of 0.1, 0.05, and 0.01, I'm dividing alpha by 2 for a two-tailed test. So I'd be looking at 0.05, 0.025, and 0.005. So I'll use those three columns. My standard normal values will be positive and negative 1.645, positive and negative 1.96, and positive and negative 2.576. So those would be these three critical values, or pairs of critical values. Now, right away with a two-tailed test, I should always know that I'm going to have these pairs of critical values, right? A threshold on the left and a threshold on the right, because evidence on either side could go against the null. So right away on 17, I should have ruled out A and C right off the bat. Okay. And then from there, we just had to actually kind of go through and look it up. Is there any questions kind of here before we keep moving? So just to be clear too, these were our alphas. So the actual areas that we wanted in each tail was alpha over 2. So that's why I looked up 0.05, 0.025, and 0.005 here, right? Those represented alpha over 2 values. Okay. Yeah.
So if it was just a right tail or like a left tail test, you wouldn't have to divide by the alpha by 2.
Yep, we look up these values because all of my alphas in one tail for a one tail test. So how would I do that? Now I'm going to go up. Let me get rid of this real quick just so I can. Now the area I want is 0.1, 0.05, and 0.01. So I'm just looking at these 3 columns now. I can go to that very last row, 1.282, 1.645, 2.326. Now the issue is going to be, those are going to be my critical values for a right tail test. What if I wanted critical values for the left tail test? It's going to be not 1 minus, right? We only kind of, take 1 minus when we're looking for the area under the curve, right? So here we've actually got the z values. So for a left tail test, it's going to be those exact same 3 values. But if our standard normal distribution is centered around 0, it's going to be those same 3 critical values, but negative. Right? So for critical values, your left and right tailed values will be the exact same. It's just that for the right tailed test, they'll be positive. For the left tailed test, they would be negative. For a 2-tailed test, it's going to be both of them. So you'll have a pair of critical values. Now that value will vary a little bit because, right, we just said, your question was, for the left and right tail test, you're just going to look up alpha. Because alpha is the total area just in that one tail. When I have 2 tails, I need to look up alpha over 2 because alpha is the total area in my tails. So there's half of alpha in each one. Any other questions? These are good questions. So, all right. So keep working here. So the next question is, what's my test statistic? So if I'm thinking about calculating my test statistic and I go to my formula sheet, I have 3 test statistic equations here. 1 for my sample proportion examples, 1 for a sample mean where I know the population variance or standard deviation, 1 for the sample mean where I only have a sample variance or only have a sample standard deviation. Now, in practice, it doesn't really matter if I identify the incorrect sample mean because once I plug my values in, it looks no different. The sample proportion is a little bit different there. But we know for us, we should be using one that has a known population standard deviation or variance. And it kind of reminds us, okay, then that test statistic is going to be representing a z value or coming from the standard normal distribution. Okay? So what we've done here is say, okay, look, I use this assumed true value for the mean. We go back to our known alternative of 105. Okay. So the assumed true mean is 105. So my sample means should be normally distributed around that if in fact it is the true value. The sample mean we saw was 109. So that was the sample mean value we found. So if I'm looking at this here, if I'm coming up with a test statistic, remember that test statistic is just a z value, right? It's telling me the number of standard deviations away. So it's coming from a standard normal distribution. When I convert this value into a test statistic, or more specifically a z statistic, a test statistic coming from a standard normal distribution, it's going to tell me the number of standard deviations away from that assumed true mean that I am. Well, if I see sample evidence above that, my test statistic is going to be what sign? Well, my test statistic will be on the right, but the sign, right? My standard normal distribution is centered around 0. So my test statistic should be positive. I'm seeing a value that is going to be a certain number of standard deviations above that assumed true mean. So when I look at those answers right away, oops, I didn't want to do that. I'm trying to record this. So when I look at these answers right away, I can rule out A and D. Right? I know that the test statistic has to be positive. Okay? And if I look at my formula, right, it kind of actually gives me another reason why I know it has to be positive. So if I think about what I'm doing here, let me see, can I get this any bigger? Not as big as it goes. So that equation that we have, right, is right here. We found a sample mean of 109, subtract that assumed true mean of 105, and then here divide by, now I was given a standard deviation of 15, if I'm recalling correctly. So when I plug this in, just like with the confidence interval, I only have sigma here. I only have the standard deviation, so I got to make sure I still square it. And then my sample size, I think, was 49. Okay. Now, if we remember that in my z-value or in my t-value calculations, my test statistic calculations, my denominator always represents a standard deviation. In this case, I'm calculating kind of a z-value for a sample mean. It represents a standard deviation of my sample means. Okay. So what's going to be true about variances and standard deviations? They're always going to be positive, right? So the lowest they can be is 0. So when I'm looking at my test statistic, the sign of my test statistic is just going to be if that sample mean value I found is above the assumed true mean, I'm going to have a positive test statistic. If that sample mean value is below the assumed true mean, it's going to be negative. But from here, it's just a matter of getting this entered into our calculator. Okay. Any questions on this? So if we look back at the answers here, I don't know what is it off the top of my head. So let me, someone beats me to it, let me know. Just, it's kind of eating into your time for review if I'm calculating these. So, oops. So 1.866 repeated. So 1.867 if we round to the third decimal. Oh, sorry, 1.867. My cursor was on the wrong one. Okay. So this is the value of my test statistic. Are we okay with this up to this point? No questions? All right, so at this point, we've got our test statistic. We could compare that test statistic to the critical values we found before. So if you wanted to, you could kind of plot these critical values, right? So I could say, and I'll kind of blow this up here in a second, but I'm just going to get them plotted and then we can kind of return. So we've got what, 1.654, 1.96, 2.326, so negative 1.96, negative 2.326. My rejection regions, that's kind of just where we're going to take those critical values, think about the area that's more extreme than them, or draw our kind of arrows in the tail. Okay. Well, now this is one where I could plot my test statistic and come up with my rejection decision, but if I got the test statistic wrong, very likely I'm going to get some of my rejection decisions wrong, right? So in problem 19, I then tell you, okay, assume you found the test statistic was negative 2.3. Another example where I'm trying to prevent from cascading errors. So you've got this test statistic of negative 2.3. All you're going to do is once you have those critical values plotted out, if your test statistic is more extreme, right, then you're going to say that you reject or fail to reject. So negative 2.3 right, is just inside that critical value for the 1% level, right? So here, we're in the rejection region at the 10% level, so we reject. We're in the rejection region at the 5% level, so we reject. We're just barely outside the rejection region at the 1% level, so we would say we failed to reject at that 1% significance level, okay? So all you're doing there with the critical value approach is you're plotting your test statistic against your critical values. Okay. Now, maybe you weren't very, sorry, before I keep going, is there any questions on what I did there? So like in practice, you would use the actual test statistic, right? But on the exam, to prevent mistakes, I'll then give you an assumed true test statistic, so I know that we're all starting off on the same foot again. Okay. Any questions on that? Like I said, this is for you guys. I want you guys to be better. So if you're having questions, make sure you ask them, okay? Yeah.
So if it was positive 2.3,
Yeah, so this is an interesting one where, actually, that's a good point. So because we had a two-tailed test, seeing positive 2.3, I'm in the rejection region at the 10% level. I'd be in the rejection region at the, 5% level, but I'm just barely not in the rejection region at the 1% level, right? So for a two-tailed test, I only see one sample mean, right? So I'm only going to have one test statistic. But if I saw something 2.3 standard deviations below the assumed true value that I had, well, that's enough to reject at the 10 and 5% level. Same thing, if I saw sample evidence that led to a test statistic where I was 2.3 standard deviations above that assumed true mean, well, either side goes against the null there, so I'm still going to end up rejecting at the same levels, regardless if I saw sample evidence that was above or below that assumed true value, because now it's just one value, right? With a one-tailed test, it's different because I've actually got a whole range of values, right, that I'm assuming that it could be equal to, right? So I'm being like I'm not being near as specific when I'm doing a one-tailed test. I was kind of hold off on this discussion until after this exam. We'll do a little bit more hypothesis testing after this second exam. And we're actually going to find out, and we'll kind of hammer home a little more, is it's actually harder to reject the null for a two-tailed test, right? Yeah.
Yeah, just to clarify, for a two-tailed test, it's going to be the alpha over 2, whereas a one-tailed test is just going to be the true alpha.
When we're looking up the critical values. Yeah.
Technically, it's like 2.576. That's for an actual percent.
Oh, did I write down the wrong value?
Yeah, I think it's
I did. You're right. You're right. I was thinking about a one-tailed test value, right? So if I go back, sorry, yeah, right. It should be 2.576. Sorry about that. I wrote down the wrong value. I was just looking at those real quick. So that should actually be, oh, sorry, you can't see that. There we go. So I was looking at the wrong value. Sorry, I should have written 2.576 there. I just looked at the wrong value there. So we wouldn't, it's still the same thing, right? It's just that we're not near as close to being able to reject, right? We would still fail to reject because we're still not in the rejection region, but yeah.
How do you know you're out of the rejection? If you go as like the 1.645 to 1.96,
Mhm.
does that let you know, like, okay, you rejected a maybe 1.645?
So think about it this way. So I have these kind of cutoff thresholds, right? A certain number of standard deviations away. If I see a test statistics are tied to the sample evidence I found. So if I saw, let's say I saw a test statistic, I'll do a different color to represent this as another, like, so let's say we took a different sample and we instead found something like 1.8. All I'm doing is plotting that test statistic. It's like, this is a number line. So I'm just going to plot where my test statistic would fall. Well, here, that threshold for the 10% level, what I was really saying was, if I see sample evidence that's more than 1.645 standard deviations away from that assumed true value, I'm okay rejecting. Well, 1.8 is more than 1.645 standard deviations, so I would reject. However, if I'm setting a threshold for that 95% confidence level or the 5% significance level, now I'm saying, okay, now my threshold is if I see sample evidence that's more than 1.96 standard deviations away, right? And because the more standard deviations I get away from the assumed true value, like the less and less likely it is for me to see something that far away. Well, now my test statistic here wouldn't quite be past that threshold, so I would say I failed to reject. I'm just drawing the arrows to like make it kind of easy to think about the rejection region. If I'm shorthanding these, if it makes a little more sense, technically the rejection region here, like it's anything to the right. I think I was just getting lazy and kind of drawing arrows and I didn't realize that I was kind of staggering them. But it's anything to the right of 1.645, I would reject, right? Anything to the right of 1.96, I reject. Well, this wasn't to the right there, so I failed to reject. Does that help answer your question?
Yeah.
Okay. Any other questions on this? I'm starting to probably add too much to the same problem here, but I'm okay with this. So something else I could have done, if I wasn't confident in my critical values, I could have said, okay, I'm going to use that assumed true test statistic that the problem gave me, negative 2.3. And I'm actually going to do the p-value approach. Or maybe I have extra time and I just want to make sure that I didn't do something bad. And I know that both approaches should give me the same answer. Well, the p-value is going to be the probability we saw something as far away, right, or as many standard deviations away from that assumed true value as we did, or anything even further that goes against the null hypothesis. Okay. So for like a left-tailed test, typically this would be our entire p-value. The problem is for a two-tailed test, I only see one sample mean, but I know that it would have been equally as likely for me to see something 2.3 standard deviations above my assumed true mean. And for a two-tailed test, if I saw something above, that also goes against my null hypothesis. So for a two-tailed test, I'll only see one test statistic. So like I won't see this, right? But I know that it exists. I know that it would have been equally as likely for me to have a sample mean that was above the assumed true value, and that would have went against the null as well. So now, if I'm using my test statistic or my Z statistic, I can find the probability I saw the test statistic I did or anything more extreme than it. But I have to remember it would have been equally as likely for me to see something on the other side. So really, the area to the left of my test statistic here only represents half of my p-value. So once I find the area in one of my tails, I then have to multiply it by 2, because I have kind of two tails of the same size to get my final p-value. So that was like the added step for a two-tailed test, is once I find the area that's more extreme than my test statistic, I then have to multiply it by 2. For a one-tailed test, once I found that area in the tail, I was done. Okay. Any questions on that? And I'll work through this and actually look it up. Okay. So I've got this test statistic of negative 2.3. It's coming from a standard normal distribution. So I'm going to go to my Z tables. Well, now when I'm trying to find a p-value, I'm no longer working in the inverse transformation, right? I'm looking up. I have an actual Z value, and now I want the area in the tail. With critical values and confidence intervals, I knew the area in the tail, and I was trying to find the Z values, right? So I've got this Z value of negative 2.3. So negative 2.30. This is an easy one. Like if it would have been negative 2.35, I would have had to go over to this column, right? Negative 2.35. But it wasn't. I kept it kind of nice and easy. Negative 2.30. The area to the left is 0.0107. Okay. So I've got the area in this lower left tail. For a two-tailed test, I still have to multiply it by 2, right, to get my final p-value of 0.0218 or 0.0214. Wait, did I go this way? Yeah. Now, if it was just a one-tailed test, I've got my p-value once I find that area in the tail, right? Because evidence on the other side wouldn't have went against the null. But for a two-tailed test, the values on the other side would have went against the null. Okay. So I think, if I can recall, what's the actual problem asked for? I think it says, so it doesn't ask for a p-value, but we could use that if I did ask you a question to find a p-value, that's how you would do it. It's a very possible question I would ask. But if you wanted to kind of come up with the rejection, what levels you reject at, the p-value approach said, we only reject if that p-value is less than alpha. So at our kind of 3 conventional alpha values, which ones could I reject at? So our 3 benchmark values were 0.1, 0.05, 0.01. Yeah, right. If it helps me to write these out, is 0.02 less than 0.1? Yep, so I reject. Is it less than 0.05? Right, and this was our, to be clear, this is the only times when we reject. Is it less than 0.05? Sure is, so I reject. Is it less than 0.01? No, it's not, so I fail to reject, which were the same three decisions we made using that critical value approach. Okay. Any questions on that one? Okay. I think if there's anything else I want to say here before we move on. So one thing that might be helpful when you're looking up p-values or critical values, especially when it's using that standard normal table, if you're looking up critical values or you're trying to find those z-values for confidence intervals, you know the area in the tail and you want to find the z-value. So this is what we kind of call the inverse process, right? So here you were kind of looking up values in the middle of the table. Or said differently, you're looking up the probabilities or whatever you want. That's not spelled even closely correct, but you know what I mean there. So probabilities of that you want in that tail, right? And you want to find the corresponding z-value. I have a hard time writing and talking sometimes. Like I get mixed up there. So that's kind of the inverse process, right? If you want to look up p-values or in different problems, like if you go back to some of those earlier problems, all we're doing is like dealing with a normally distributed variable, and you want to find the probability that if you select a person at random, their height is above, I don't know, 73 inches. So if you're looking up p-values or the probabilities of being like below certain cutoff values, this is where you kind of look up your z-value using the row and column headings, and then find that corresponding area in the tail. Okay, so it's kind of like we're working in the exact opposite directions there. But just to kind of keep it track, when you're looking up critical values or confidence interval z-values, you know the area you want in the tail, so you're looking at the values in the middle of that z-table and then going up and over to find the corresponding z-scores. When you're looking at p-values or the probabilities of being below or above certain cutoffs, you're going to have the actual z-value, so you can use the row and column headings to find that z-value, and then kind of where they cross, that's that corresponding probability or p-value that is associated with that z-value or the z-statistic. Any questions related to any of that stuff? Otherwise, I'll probably go back and even do some uniform distribution stuff just to make a couple points. Okay, no questions over hypothesis testing or what if this happened or chance that this changed? Okay. So I don't think we'll work through them today or have enough time. I worked through them in a different section, so I'll end up posting those so you can see it. But one thing I do want to mention, to just really quickly, you can eliminate some different values for the when you're looking up critical values. If I had something like I do up here, which I believe is we did a right-tailed test. If I have a right-tailed test, automatically I know I can rule out which of these critical values or sets of critical values. Yeah. For a right-tailed test, know the critical values have to be positive. For a left-tailed test, if this was a left-tailed test, I could rule out B and C. I would know the critical values have to be negative. So when it comes to identifying these critical values, almost every time I give you options to where as long as you know that right-tailed test, positive critical values, left-tailed test, negative critical values, two-tailed test, pairs of critical values, you can almost always rule out 2 of the 4 answers for those, right? I mean, that's, base level understanding of what we're doing there with the critical values. You can already make it a 50-50 shot. So we'll go back and I'll do some of this uniform distribution stuff just because I haven't seen it in a while. and it should be easy points if we just kind of do a little bit of review on it, right? So we've got this situation. We're thinking about the waiting time in line for a roller coaster at Six Flags, and the waiting time is somewhere between 15 and 75 minutes, right? Uniformly distributed. So I first ask, what's the mean? And then the second question is, what's the variance, right? So when we're doing a uniform distribution, kind of we said the setup was like, it should be a horizontal line. Everything is equally as likely, or any equally sized interval is equally as likely if it's uniformly distributed. So we identified kind of our minimum and our maximum here, or notationally, we were kind of calling this C was the lowest point of my uniform distribution, D was the maximum point. Okay. So if I go to my formula sheet, it's organized, which is pretty nice of me, right? In order of how we've covered things. So if we go all the way back here, I remind you, first of all, that the standard deviation is always just the square root of the variance. I also remind you, here's your uniform distribution equations, okay? So here's the mean, here's the variance, right? So it's just a matter of plugging our values in. So here, if I want the mean, all I'm looking for is the middle value. Well, if I know where something starts and stops, and I just want the middle value, I'm basically just taking the average of the two. So I add those two values up, divide by 2, and I get my mean of 45. Right. Any questions on that? Make it a little bigger here. So hopefully, just like on the first exam, I want everybody to get this first question right, right? And other one was calculating a mean of just a small data set on the first exam. Here, we're just gonna, I can almost guarantee you that first problem is gonna be find the mean of a uniform distribution. Okay. Shouldn't even say almost guarantee you. I can't guarantee you, okay? For the second one, what's the variance? Well, once again, we've got that batch of uniform distribution equation here. It's just take that minimum, C, add the maximum, which we're kind of notating as D. Oh, sorry, not add. I just screwed it up. I was looking at the mean. Take the maximum, subtract that minimum, square it. So take the range of values, basically, maximum minus the minimum squared, and divide by 12. Okay. Now, if we looked at the problem, it asks for the variance, right? So I think if we do this, it'd be what? 60 squared, 3,600 divided by 12. I think it's 300. I'm doing the math in my head correct. Now, the only other thing I might do is instead of asking for the variance, what if I asked you for the standard deviation? It's going to be the exact same thing, but I just have to take the square root of the variance, right? So it'll be the square root of 300, which I'm going to go out, I think is probably the 17.32. But I didn't ask you, this one for the standard deviation. I'm just saying I could, wink, wink, do that on the exam. Any questions on those two? Those two should be like, hopefully setting you up for some success there with those first two problems.
So, in the description above the questions,
Mm-hmm.
you specifically state if uniformly distributed.
Yeah, sorry, this thing's in the way. Yeah, right, it's uniformly distributed. And also when we write this out, we kind of, X is uniformly distributed as opposed to normally distributed.
I don't know if you're gonna have just the notation or.
Nope, I'll have both. Yep. Any other questions here? All right, 3. Oh, did you have a question? Okay, okay. What's the probability that person waits in line for more than 50 minutes? So one thing that we actually, once we first draw out our uniform distribution for those first few set of questions, we can always identify the height, and the height is always going to just be 1 over D minus C, or said differently, 1 over the maximum minus the minimum. So for us, that's going to be 1 over 75 minus 15, or 1 over 60. Right? So I can always find the height of my uniform distribution by simply taking 1 over the range, or 1 over the maximum minus the minimum. Okay. That is, I'm kind of reminded of that on my formula sheet. That's kind of what this is saying, right? Within the values between my minimum and maximum, the height of this distribution is 1 over D minus C. If I'm outside that range, it's 0. That's just to be complete. You can actually kind of, ignore that. It doesn't make any, If I know that the weight is somewhere between 15 and 75, what's the probability it's greater than 80? It's impossible, right? So I tell you the maximum is 75, but it can't be 80. So the probability would just be 0. Right? I won't do something like that in the exam, but so I want to know what's the probability it's greater than 50. All I'm really thinking about there is what's the probability that this is greater than that value of 50. It's going to be represented by this area, the area under the curve, but to the right of 50, up to whatever the maximum is. Now, I've just got the area of a rectangle. So I know the height is 1 over 60. I know the width, it goes from 50 to 75. So just times 25 there. So this is what? 25 over 60, so 0.46 or something, or I don't know, somewhere around there. We'll see once we go to the answer key. All right. But right away, when I was looking at this one, what value did I know the probability of being greater than 50 has to be less than? What area would be to the left and the right of the mean? The uniform and the norm are symmetric, so the areas to the left and right of the mean is, someone said it, well, the width is 30, but sorry, I shouldn't say area. The area under the curve, but to the right? The probability of seeing something above or below the mean would be 0.5, right? So the probability I see something above or below the mean should be 0.5. So if I was thinking about that, that would be this entire area. Well, I wanted something smaller than that. So right away, I know this probability should be less than 0.5 if I just kind of draw this out and think about where that mean is at. Okay. Now, so if I look at here, I could have ruled out B and A. Hopefully, nobody answered A on this question, right? Because what am I looking for? A probability. What's the greatest it could be? Yeah, if I said, what's the probability it's above 15, then at most it could only be 1, right? So 1.25 doesn't even make sense here, okay? Let me think. We could do this next one. It's basically the same idea. It's just that we're looking for between two different values, but I'll show you something else that maybe I would ask you to do. So I'll change this problem a little bit from what it is, just so that maybe it's a little more useful for the exam. So let's say I wanted the probability it's between 30 and 45, okay? So here, I'm gonna start out with everything that we had already had. We had the height was 1 over 60. That mean, let's say that mean was 45. I don't know if that'll be useful, but maybe. So I wanted the probability it's between 30 and 45. If I was actually answering this question, right away, I know this has to be less than what? The area to the left of the mean would be 0.5, or the probability of seeing something below the mean is 0.5. I want something smaller than that, right? So hopefully I could rule out everything that's above. So I could rule out actually B and A. So I know it's going to be either C or D here. But let's instead say I wanted to know the probability it's between 30 and 45, or between 60 and 75. So is it in this range or is it in this range? Excuse me. Well, what I could do is say, I'm just finding the area of a rectangle. So the height is 1 over 60. The width, 45 minus 30, or 15. So this is going to be what? 15 over 60, which should be what, 0.25? Well, what's this area going to be? Has the exact same width, 60 to 75, to be the same width of 15. So I don't even have to go through the process of finding the width, calculating it by the height, because I know for a uniform distribution, equally sized intervals, they all have the same height, so they're all going to have the same probability of occurring. So if the probability I see something between 30 and 45 is 0.25, automatically something that has the same width, 15, I know the probability I see something in that range is also going to be 0.25. Now I can go ahead and, take the height, multiply it by the width, and I can prove that to myself. But if I'm on the exam, so way to save time, if I identify that these are the same length interval, once I find one of them, I automatically know the other. Right? And so then if I want the probability of being in this range or this range, simply add those together. Right? Any questions on that one? So that would be if I change the problem to instead say, what's the probability it's between 30 and 45 or between 60 and 75? Okay with that? All right. So we got 15 minutes left. You guys want to see any type of problem or specific type? Otherwise, I'll probably just work through the next couple on here. But if there's like something specifically that you're kind of confused on or want to want to see an example of, I'd rather use this time to do that. So I want you guys to do really well in this exam. Okay. Let me actually, I told you I wanted to do this, and of course I didn't bring the stupid things I forgot. If you guys don't mind on the way out, would you write your name down on a piece of paper for me? I really am interested to see the correlation between attending the exam review and performance on the exam. So if you don't mind on the way out, just jotting your name down. I'll put a couple pieces up here too, so it doesn't take as long. But I'll work through a couple more problems before we get there. Okay. All right, so probably cut that out of the exam review. People that aren't here today won't be very happy about that. But I really am I'm just curious for my own uses. So on problem 5, I'll probably do something like this. Different example, obviously. But I'm going to go all the way back to when we very first started, right after uniform distribution. We said, okay, let's just talk about variables that are normally distributed. So here I kind of used the amount of student spends on rent, right? So here I'm thinking about, okay, I've got this normally distributed variable, and the mean is 460, and the variance is 10,000. Now the variance is useful, but a lot of the times it gets more useful to have the standard deviation. So just right away, I'm going to figure out what the standard deviation is as well. So I know the variance is 10,000. The standard deviation should just be the square root of that, which would be 100. Okay. Any questions on that? That should be fairly straight. I mean, we've got a normally distributed variable. We know the mean. We know the variance. We could determine what the standard deviation is. I then say, okay, what's the probability that I see rent be above 600? Okay. Right away, I know that probability has to be what? Less than 0.5. Same thing. Probability of seeing something above or below the mean, 0.5 on either side. I want something much smaller than that. Okay. So before I even go ahead and turn this into a z-score, because in order to find that probability, I need to convert that value of 600 into a z-score. Right? I know that it should be less than 0.5. And also, if I remember the definition of a z-score, this one's actually kind of a nice, easy example. Because if I have a standard deviation of 100, the z-score is telling me how many standard deviations away from that mean the value I'm looking at is. So if I've got 460 as my mean, how many standard deviations away would 600 be? Yeah, it's 140 above. The standard deviation is 100. It'd be 1.4 standard deviations. Now, if the numbers weren't as nice, I've kind of got, if I just dealing with a normally distributed variable, I can use this equation right here. So I could take that value of 600, subtract that mean, divide by my standard deviation, right? And I sure enough get 1.4. Now, I told myself ahead of time, it can't be greater than 0.5. It has to be less than. So I could cross A and B out right away. Right? From there, I just need to look up that z value on my standard normal table, so this is another situation, I have the z-value. I want the area in the right tail. The table always tells me the area to the left in the left tail. So when I look up 1.4, which would be 1.40, right? The second decimal of 1.40, 0.9192. So I know the area to the left is 0.9192. If I want the area to the right, what do I have to do? Simply, I think someone said it, subtract it from 1. Also, it's very interesting human behavior. I do it too, but like almost all of you will say 1 minus. It's just so funny. Like, it's so funny that you wouldn't say you subtract it from 1, or like we always say 1 minus, but that's what you do, right? You take that area to the left, you subtract it from 1, or 1 minus that area to the left. Okay. Now, if I had forgotten that step and I just, I found the 0.91 from the table, that must be it. If ahead of time I had drawn this out and said, oh yeah, it doesn't make any sense for this to be above 0.5, and I cross these out, then I go to answer 0.91, I go, wait, I crossed those out because I'm looking for the area to the right, and I can kind of maybe remind myself I still need to subtract it from 1. So sometimes like drawing these out and thinking about which answers you can rule out prevents you from making like really easy mistakes, like forgetting a very simple kind of step at the very end. Okay. For the sake of time, I'm not gonna do 6. It's very similar. We're just looking for different areas here because I want to make a little bit more of a point to what then happens if we start dealing with sample means, right? So this question, right, is now what's the probability it's less than 400 or above 520? Well, there we will be looking for kind of 2 areas. We convert those values into z-scores. We could find those 2 areas, add them together. It's going to be very similar to this process. Okay. So if instead I go down here to problem 7, this is the one area on the exam where I can't really prevent you necessarily from making cascading errors. So this becomes a really important question to know how to be able to solve, right? And I can guarantee you'll see one that looks a lot like this. So I gave you a normally distributed variable. And then in problem 7, I'm saying, okay, let's assume that you then take a sample of 25 students, right? So now I'm thinking about the distribution of my sample means. Well, the formula sheet reminds us that the variance of my sample means is the variance of the original data I sample from divided by the sample size. So as long as my sample size is above 1, the new variance of my sample means is going to be lower than the original variance that I sent, of the data I sampled from, right? So I'm going to be dividing by something greater than 1 that's going to drive this down. Okay. So my original variance was what? 10,000. My sample size was 25. So I can determine what that variance of my sample means is. And then from there, I just have to remember my sample means will always be normally distributed around whatever the original population mean was. So I'll have a very similar setup on the exam. I'll give you some normally distributed variable, ask you a couple questions about it. I'll then say, okay, you took a sample of a certain size from that variable. What's the mean of those sample means? And what's the variance of those sample means? Well, the mean of your sample means should always just be the mean of whatever the data you sampled from was. So for us here, that would just be that 460, right? From there, it's just a matter of knowing the variance of your sample means is the original variance of the data you sample from over your sample size. So if we do that here, we should get 400. One other thing I might do on that problem is instead of asking for the variance, ask you for the standard deviation of your sample means, which would just be one more step, which would be to, if I want to go from the variance to a standard deviation, I just take the square root, which I think that gives me a standard deviation of 20. Okay. Any questions there?
Is there any extra question?
I'll probably be nice. Yeah, probably be one on there. Any questions on this? So one more thing, then I'll kind of let you guys go. So this next problem, I then ask you, what's the probability you're between 475 and 500? Oh, sorry. What's the probability you're in between 475 and 500? Well, now I'm thinking about sample mean values, so I'm over here. Right? But it's now going to be the exact same process. I turn these into z-values. Right? Once I turn these into z-values, I then could look up this z-value, find the area to the left, look up this z-value, find the area to the left. If I wanted the probability of being in between the two, I'll just take that smaller area, subtract it from the larger area, and I'll be left with what's in between. Now, to convert those values of 475 and 500 into a z-value, I go down here. Nope, not down here. Must be at the very top. And I'm reminded, when I want to turn sample means into z-values, this is the equation I use. And the reason why is because it's really the same process as what we were doing before. It's just that now this represents the standard deviation of the statistic that we're interested in, right? So I would take those values, 475, subtract the mean of 460, divide by, now I could plug in the population variance and the sample size, or if I had calculated that standard deviation of my sample means ahead of time, I could just plug 20 in here, right? So kind of two different ways of doing the same thing there. Once I come up with those z-values, like I said, look them up in that standard normal table. You can find the area to the left of each one, subtract the smaller probability from the larger one, and we'll be left with kind of the probability I'm in between these two sample mean values, or in between these two z-values. Okay. I walk through this one in a little bit more detail in another section, so I'll probably splice some stuff together so that I have like one big file of me working through every problem on this practice exam. And that will have me kind of working through this a little bit in more detail. So if you're going over it and you aren't sure. Other than that, I'm going to have these up here. If you guys don't mind, so write your name on the way out. And I will see you guys on Wednesday. Also, I'll be around my office tomorrow. My office hours are 11 to 1. But if you have another time that works better for you, send me an email and we can set something up so that we can get that kind of worked through. Or set up a time, sorry.
Can I borrow a pen? Oh, thank you.
As I said, you can take one of these Sharpies even if you want.